All right, I apologize kind of for the abrupt ending of the last time. I think we finished here at question 5, but all of a sudden it just stopped. I mean, sometimes the QuickTime video it gets overloaded, especially when I have my ladybug on, and that's what happened. But luckily, it saved those 3 minutes. I didn't have to redo them, which always keeps me from swearing. But anyway, so a hockey player is on a very large lake. He smacks us at 100. The puck has a mass of 0.17. We're assuming the puck was at rest before it was hit. Calculate the kinetic energy of the puck. All right. All right, now you got to be careful. Got to be careful. 106 miles per hour. What's the first thing? So to do question 6, let's take this step by step. All right, so on question 6, 4 and 5 are easy. So question 6, kinetic energy is equal to 1/2 mv squared. Be careful, novices to physics. They said the speed was 106 miles per hour. That's an issue. But we have our good old conversion factor, right? All right, to be scientifically correct, I went ahead and added the hours. Hold on. I went ahead and added the. That looks clear on my hand, but that looks fuzzy, doesn't it? I think we need to focus this sucker. It's still seems kind of funny. There, that's a little better. All right, I think. I'm not sure. I'm sorry to be wasting your time. All right, so anyway. That's the brightness. There we go. That's a little better. Okay, good. I found the focus. Sorry about that. Wasted your time. So multiply just 106 by 0.447. And that'll give you your meters. I was just being silly here. To getting our miles per hour, meters per second. And that'll give you your meters per second. And then you'll know the kinetic energy with the kilograms with the mass equal to 0.17 kilograms. Okay? So then you'll have the velocity, you'll have the mass, you can compute that without much trouble. All right? If the puck was pushed by the stick, we're assuming it was at rest before he hit it, for 4 centimeters, how much force did the stick apply to the puck? This is huge. It's going to be what I call a BAN, big ass number. Because look. Because force times distance is equal to the kinetic energy, or the work done. All right, force times distance is equal to that change in kinetic energy. We know this distance, but remember we said it's 4 centimeters. What do we need to do? Convert that to meters. So you divide by 100, because there's 100 centimeters per meter. So those go away and you get the meters. So it's 0.04 meters. All right. So how do you get F by itself? You know KE from problem 6. This is the problem 6 answer. And then you divide that by D. That's the way you get it. And then you'll get your force. Okay? And it'll be big. It'll be big. This ain't no party. This ain't no disco. All right, anyway. So now, if the puck comes to rest after being hit in 700 meters, all right, so it comes to rest in 700, what is the force of the friction the ice is applying to the puck. So it actually comes to a stop. So now you're going to find the force of friction. So it came to a stop within 700 meters. All right. So what is the force of friction when applying? All right. So some of you are going, yeah. You've said that. You've read it 4 times now. Do the damn thing there, doc. Okay. Well, trust me. I'm a doctor. Anyway, so here we go. So we got 8. Okay. So the same thing here, except this time the force is negative, but I think you can put it in a positive force, because here's physically is what's really going on. Puck is flying, we're going to assume this way. Started off at 106 miles per hour initially, right? V final is equal to 0. Right, so it eventually comes to a stop. So there's a force working on this guy, and that's called the kinetic frictional force of the ice. That's the kinetic frictional force is working against it. And so, because it displaced a certain distance, which is what we're trying to find, it displaced 700 meters, but the force is working this way. F of k is working this way. So what do we know? The acceleration on this thing had to be negative. And we haven't gotten too much into F equals ma. We watched some of those videos about it, but F equals ma. So the force is negative. The displacement is positive. So physicists get all, we get all twisted in a knot over this stuff because it's important. So it's taking energy. Does it make sense to you that it's taking energy out of the system? So the amount of work that it's doing is negative work to slow it, to bring to a stop. Long explanation for you're going to do F of k times 700 is equal to the kinetic energy from problem 6. And you're going to solve for F of k. And I don't think you need to make it negative. Okay? I'm going to stop here and go on to the and do another one, because